Okay, so let's start lecture 4. We plan to learn very basic concepts of 2D, not actually 2D, any D other than 1D. But I realized when I was preparing for this lecture in the morning that before we can actually talk about 2D, even without any mathematics, I'm not going to use any math there for the 2D because the math of 2D is a bit involved. I do not want to do that. Rather, I'll be using a little bit of um, examples from other world to help you understand how 2D works. But even before that, we need to do certain things. So we'll start from there, and then slowly we'll go into the 2D today, and then I'll tell you how 2D works for NMR. So the most important thing that is going to be here is that this concept that we had this resonance, correct? This is something that we have found out last class, that this omega AC, which is the gamma times B1. So this is a gamma times B1, and B1 is the small field, which is the RF field, radio frequency field. That is omega AC, and that should be ideally be uh, uh, equal to the Larmor frequency, which is gamma times B0, where B0 is the main field, but exactly not B0, because we have learned also in the last class that the Larmor frequency is not only gamma times B0, but also this is the most important part, and then we call it the chemical shift. So what happens is that even for the same B0, same gamma, means like different protons. So protons had a particular gamma, carbon-13 has a different gamma, but within one type of proton to another type of proton, gamma is same, B0 is same spectrometer. But even then, as the sigma, the chemical shift is different due to the environment, the local environment created by the electron cloud is different. This Siemens splitting becomes different because there's delta E, which we have found out last class also, that omega 0 H cross is the delta E. Now, if the omega 0 itself is changing, correct, so you have delta E slightly different from thing. So here I have tried drawing three different situations. Suppose there are three different protons in the same molecule having three different chemical shifts or shielding effects, correct, and then we can clearly see that as we have a larger sigma, correct, this whole 1 minus sigma becomes smaller. As the sigma goes up, this 1 minus sigma is smaller, and hence omega 0 is also smaller. So therefore, I can see this is the smallest amount of energy difference, and hence sigma 1 is the largest. So this is basically the ordering. Now the question is that this resonance that I was talking about, we have a certain B1, gamma is given for protons, certain B1 we're creating, because this B1 is a magnetic field we are creating using an electromagnet in the RF coil. This is a different coil. This resonance frequency cannot be satisfied simultaneously for three different omega 0, and not only three, but in a molecule which is very complex, you might be having 100 different types of protons, like different peaks, right, which ultimately will be coming as different peaks. Now the question is that how can we make this particular resonance condition satisfied for different types of protons which has different chemical shape? So this is one big problem. So this one. So first we have to understand this too, that how this was done. First we will be learning how it was done previously, that means in the old generation of spectrometers, and then how it is done now, because unless we understand that, we cannot actually move to 2D. So if we can draw this one, let me just try to draw something for you. So I have a B0. Let me remove this and make it black. Fine. So this is the B0. Suppose I can change B0. What happens? For a given B0, suppose this given B0, right? I can take this particular line. And what I have drawn is that it is the energy, this particular level. So basically this particular level, this is the top level and this is the bottom level. We have already seen that this top level is called the beta and this is called alpha, correct? The lower one. So I have just tried to draw this beta and alpha, and the separation between the beta and alpha, correct, is progressively increasing as we are increasing the B0, because obviously the delta E between the two levels is proportional to B0. So therefore, if the B0 is changing, then the omega 0 is also changing, and hence the delta E is changing. So I have just tried to plot the separation between these two levels, right, as a function of B0. Now this is basically the situation. Now if I have another spin, let me bring it down. Have to, let me just bring it down a little, this much. Okay. Now suppose I have another one, and this one is something like this. Well, please excuse me, it has gone below this particular thing. It is not supposed to, it's not supposed to go below this line. Not supposed to go below this line. Yeah, now it's better. So what happens is that I now have two different spin for the same from the same level, some similar B0. Now I have, this is the energy gap between, for a particular spin, and then this is the energy gap, which is a larger energy gap for different spins. So exactly the same thing that I had drawn here, the two different sigma, and giving two different, for the same B0, it can give a little bit of different separation. That is, I had tried drawing it, correct? Now the question is that how we can satisfy this resonance condition at the same time. So this particular thing is done two ways. One way is that earlier it used to be done, and that is called a continuous wave. What do you mean by continuous wave? It simply means that this particular omega AC, I'll be making fixed, and it's continuously I'm irradiating into the sample given a particular B1. I'm not changing this, so therefore I'm giving certain amount of energy, right? That particular energy is basically fixed, correct? So what I mean is that let me just try drawing that particular energy. So this, like, suppose this is the amount of energy I'm giving. So this much energy I'm giving to the thing. So this is because this is the energy scale. Obviously, this is E. So this much energy I'm giving, that is coming from your this delta E, that is coming from your H excitation, some excitation energy I'm giving with a radio frequency. Now, once this is happening, I can see that with this particular energy, right, this particular energy will be giving me exact resonance condition for this red line when this B0 is like, so this dotted line is matching with this particular level and this particular level, correct, this particular level. So I have this B1, which is here, and this B1 is actually for the red one. So this B0 is for this red one, right? I can call it B0R for the red. Whereas the same energy, this much amount of energy will be useful for the resonance condition when this, for the blue one, where I have the B0 here, because for this particular B0 here, this dotted line, black dotted line, is cutting this to the blue one. So therefore I can draw another one. So this means that, okay, this is B0 blue. So that means I have, for the same excitation, continuous means continuously I'm irradiating this particular sample, and with this much energy gap, I'm having when the B0, the main magnetic field, is this particular value, then I am having this red one resonance condition satisfied. But when the B0 is shifted to this value, then the red one is condition is there. So this is called the continuous wave. So what happens is that we have a particular amount of irradiation given, and then we are sweeping we are sweeping the B0. So we are sweeping the B0. This is the B0. We are sweeping from left to right. And at some point of time, when this particular value is exactly matching to this B0 blue, and then sometime it will be matching with the B0 of red, then I'll be getting two lines, correct? So I'll be getting one line. I'll be getting one line here, and I'll be getting another line here, because that time this particular energy is going to be absorbed, correct? And I'm getting line. So therefore, as I'm sweeping the B0, the main field, from left to right slowly, correct, the moment it hits the exact value for which this particular Zeeman splitting for the blue one exactly matching with this particular thing, I get a transition. Then again I'm changing, and then comes this one where it is matching with the red one, it is changing. So this is called a continuous wave, and this is basically the original spectrometer long back, even before I was even born. That time we had the spectrometer which were working on this particular way. But the bad thing about this is that this process is extremely slow, and more importantly, this process cannot give 2D, 3D, 4D, anything. So it's just simple 1D. Just scan from left to right, sweep it, sweep the thing, and then continuously irradiate this. That is why it's called continuous wave. And then just try matching thing. This is the thing. This is bad. This is slow. So Richard Ernst, who won Nobel Prize, he thought that, well, this is not the good way to do it. So what we should do is that we should do this particular thing. So let me try drawing this particular thing again, because I have made it very messy over here. So I have to draw it again. Oops. Okay, I have drawn it. And therefore, I have now, the thing is that B0 field is like this. This is my B0. Correct? And I have two different situations. So what he told is that fix B0, don't change B0. So earlier we had fixed excitation energy, we sweep the B0, because earlier days it was electromagnet. It is very easy to sweep the B0 field, just change the current and it will be done. But now we have superconducting magnet. It is, once it is charged for a given B0. We do not change it. So my B0 is fixed. So now if my B0 is fixed, what I can do? So B0 is fixed. Fine. So therefore, I have to now give irradiation, right, of two different frequencies. One frequency is one, and energy is this much. This much energy will actually make the red one. Okay, I can draw it with the red. This will excite the red one, and also I should give another energy at the same time. This much energy will excite the blue one, and I have to give them both together. So what we are doing is that instead of sweeping this, and instead of having a fixed one, we are giving a small pulse of B1 energy. So that pulse is a small pulse like this of energy, right? And then if you just Fourier transform this, basically the energy, what are the different frequencies are actually giving this energy, has a wide range of frequencies. There are so many different frequencies. The new EX I was talking about earlier, the new EX was fixed. Given one single frequency, that is a single energy I was giving. So new EX was fixed, B0 was sweeping. Now we have B0 fixed at a particular, this is defined by this, and then I'm giving a pulse, RF pulse, which has an energy response, that it is giving energy to a large number of very large number of things. So we have at least this much amount of this entire thing is giving a lot of energy giving. So this entire range giving the, then if I have two frequencies, one is red frequency, another is blue frequency there, right? Both of them are getting at the same time. Now the question is that, fine, I have then excited them together, but then what happens is that if they are excited together, then I have two different tiny magnet, bulk magnet that we have learned, both of them are created at the same time. Right? Both of them will be created at the same time because we have excited them both. Both has been flipped from the Z axis to the XY axis, done simultaneously. How would I then understand the frequencies? Because this is going to be a frequency. Oh, sorry, this is a red. So I'll put it. This is omega 0 R, a different red, and then this one is omega 0 blue, which is a different. These two are not equal. So how, and then both are giving me the FID. Like one is going to be a blue FID, and another is going to be a red FID. Maybe we can have another third spin which has even a smaller FID. And you can have basically maybe another which has a very high frequency FID, and all these FIDs together will be mixed, and then you will be getting a signal which is basically a mix of all. And this signal can only be separated out using something called Fourier transformation, correct? So the Fourier transformation is the one which will be giving you, if you just fit this particular thing, a mixture of frequencies. Basically it will give you a spectrum which will be looking like this. So this is going to be the frequency, and then you'll have different peaks, right, at different frequencies. What are the frequencies which are present over here, it can actually give. So therefore, instead of having this particular same picture like this, correct, by slowly sweeping the B0, then it is matching, then the one again it is matching, then another one, I'm giving energy to all of them, and then I'm just analyzing them Fourier transformation, and like this. So my my NMR the PI, my PhD guide, he used to give me a nice example for this particular thing, because he was the person who was with Richard when as a postdoc when all these things were getting developed. So he used to give me one particular nice example. He said that if you have to find out the frequencies present in a piano, correct? So the piano has a different keys, correct? Or each key has a slightly different frequency. We can hit them one by one. So what I can do is that either we can first hit this one, I record the sound, analyze it, okay, what's the frequency, and note it down. Then I hit the second one, and then I can do it. Or instead I can hit all of them together, and then what is going to come out of this is basically a noise, because it is going to be a mixture of all these frequencies and together, and then it is going to be a noise. But if I can record that particular noise and Fourier transform, I can actually get all the frequencies present in the piano. So this is basically exactly the same thing that has been done. So nonetheless, once this Fourier transform NMR was done, then people have started thinking, so the Fourier transform can actually make life easier, because we can now do something called 2D. I'll be coming to the 2D by the end of the class. But even before that, I need to tell you another concept in a very brief, and that concept is called a J coupling, because unless we know J coupling, we cannot understand 2D. So J coupling, let me just talk about J coupling briefly. This J coupling, as you'll be studying again. So J coupling is, I'm just going to be giving the theory of it. J coupling, the usefulness of J coupling, you'll be learning again later on. Okay. So what happens is, suppose I have a situation like, for example, let me take a very simple molecule like CHCl3. And now I'm having this particular, suppose this is a 13C level CHCl3, so there's no problem with this. It's all 13C. So this, if you just look at this particular situation, so we have a 13C, and we have a proton, it's a smaller one, different color. Okay, now this particular one, we have the bonding electron, the bond that has been created. So I can actually draw those two electrons, if you think this way. Well, I'm not supposed to draw exactly electron in a 2-point charge like this, but nonetheless, this is, I can draw, this is one electron over here, another electron over here, and they're suppose creating the CH bond. Right? I'm not talking about the Cl3 for the time being. So I have a nice two different spins. I can call them A and B as well if you do not. Okay. So one thing is that this is, suppose both are spin half. So this is also spin half, this is also spin half, and therefore this particular one is also having two different levels, and this is also having two different levels. right? So alpha beta, so this is beta, this is alpha, this is beta, alpha, etc., etc. Now this particular spin A can be either in the beta or alpha, and then we'll see that we know if it is in a beta, then it's slightly higher energy, then it's alpha and slightly lower energy, we know it. But let's start with this particular situation. So suppose this A is in the up state. Let it be an up state at some point of time. Then it can be shown through the contact shift interaction, which I'm not talking about. It's like some kind of hyperfine interaction. I'm not going into the detailing of this particular theory, but it can be shown that this electron, which also has a very large magnetic moment because it has a spin half too, that particular one, if it is a down spin, then the energy is less. So they are kind of pairing up, correct? If this is up, then this one down is going to be a lowering of energy. So suppose this is in this particular state, but these two electrons now in the same MO, correct? Therefore they will have to have the paired up spin. So I can only expect this electron to be plus. Now this nucleus, the B nucleus, has two choices. Either it can be having the up or it can be having down. But the energetically favored situation is always going to be this one is down, because then, well, everything is perfect. This is up, so this is down, so up and down making a slight lower energy. These two has to be paired up because they're in the same MO. And again, if as this is up, so this down is slightly lower energy. But it doesn't have to be that they have to be like this. They can be independently taking any particular value. So this one, where you have this two situation up and down, it is basically giving a slightly lower energy, rather than if now it takes this one is plus, that means when both of them are up, correct, it is slightly higher energy. So therefore you have a two spin situation, then as if there is a coupling pattern is going on, that is this coupling is mediated through these electrons in the bond, such that their relative alpha beta situation is going to give us different energy. So if you have alpha here and then if you have beta here, that is going to be a different than alpha and alpha, something like this, right? So this is going to be a slightly different situation. So this particular thing is called that, as if you have a coupling, is called a J coupling, and this J coupling gives this particular situation. That means if I have a two spin system, then I do not really have only four different two different levels like this, but rather I'll be having four different levels depending upon which one is what. So if you have both alpha, both beta, etc., etc. So these are the different four levels we will be getting. I'm not going to the detail again, but this coupling it's called J coupling, and we'll be learning a lot more about this. But the thing is that one good thing about this J coupling is that if I have this J coupling between any two spin A and B, I can exploit it to do something is called coherence transfer. So this name I'm giving because these are the names that you need to understand this 2D, but I cannot really go into the full detail of math because I don't want to do this. So coherent transfer, I just give you the names few. What is coherence transfer means? It simply means that if I start with this A, I pulse on A, so therefore you get a tiny amount of magnetization, which is the bulk magnetization number A. So this is your A magnetization. And then if I have a J coupling between A and B, so you have a J coupling, then even without doing direct pulsing on J, you can actually transfer this XY magnetization to the B, and that particular thing, this magnetization will start coming. So this particular thing is basically called coherence transfer. That means that if I start with the transverse magnetization, I call transverse or like TR. So I have called transverse magnetization of A, and then what happens is if I create the transverse magnetization and then I leave it for some time, what it will do? It will do a precision, Larmor precision. It will do, like for example, it will do some cos omega 0 of A spin some time t, correct? So this will be, and then after some time when it is just taken this particular amount, if I just transfer it to the B, and then what will happen is that after it is in B, and if I leave it for some time, then it will again start precessing, but then it will precess with the speed of the B. So therefore, what happens is that we had started with TRA, already some amount of is done, and then it will start transfer the B with some other time tau. So therefore, if I now have a situation like this, I'm slowly coming into there, that if I have a pulse, a 90-degree pulse, pi/2 pulse that I was talking about, and then suppose this particular, you have just leave a particular time t, correct? And then what happens is that if this is creating some A, so therefore this magnetization having a frequency encoding like this is called frequency encoding. That means it has just taken a, it will be a cosine and sine, correct? So it will just frequency encoding. And then you can do another, do something here. So you'll be doing something here, something. Then what will happen is this will transfer to the B, and then if you have another time, correct? So I have another time, so I can get T prime, correct? And then this time it is going to be the frequency B. So this is going to be happening, and this is particular thing is done all the time in the 2D. Is this particular thing. So before going more messy like this, let me give you a nice presentation which I generally give to people who are learning 2D for the very first time, and I have just taken this from here. So you can see that this is something that I used. This KIT University is there in Bhubaneswar. I gave this there last time, so I just taken quickly the slides from there. I should have removed this name, but anyway, I'm sorry about that. So what is this particular thing all about? It doesn't look like NMR, correct? But here is, suppose I have 5 friends, A, B, C, D, correct? And E, 5 friends there, and this is their name, correct? So this is basically called identification. I'm identifying a person with a particular name, right? Identifying them. And then I'm going to compare them. After I have identified them, I'm going to compare them using marks in some exam, maths or anything. So A has got 50, B has got 90, blah, blah, blah. Now, if I just plot the same thing, what I'm doing to this is that I'm saying, okay, fine, I have done this. Now let me just plot it. And if I just do the plotting, I find that this, what is coming out, in one case is the name, which is basically the identification, and another case the marks, which is the comparison, and this looks like basically a spectrum. So a spectrum, any spectrum is actually about like this. So in one particular direction you have identification. So in this particular NMR spectrum, the identification is done by the Larmor frequency of different chemical shift, by each type of proton has a different Larmor frequency. So therefore, in this particular direction, we'll be having all the Larmor frequencies, and in each Larmor frequency, a particular proton, if that particular Larmor frequency is present, then that will give you a peak. So and that peak intensity is going to be corresponding to different thing like intensity or concentration, many things. That is, some comparison will be there. So this particular thing is there. Now, question is that this is all fine, right? Looks like it is a spectrum. Fine. But now, if I have a situation like this, that I have the identification, but now look that I have a problem because I have 2 of these names same. So that means I have an identification problem. Her name is also B, her name is also B. So therefore I have an identification problem. So although I have a comparison, these 2 lines are exactly on top of each other. So now I cannot identify them, that which one is what. So this is a situation that will be you'll be getting it when we have either 2 spins has exactly the same chemical environment, that their peaks are on top of each other. So in that particular situation, we have an identification problem. And whenever you have identification problem, we need to do something that is basically the solution is 2D. And here also I'm going to give you the solution. And the solution is that you need to bring another correlation. So basically this is called correlation. One is identification, name, 2 names are same. Then I have comparison, marks, and then I have correlation. What is the correlation? Correlation is who is friend with whom. Suppose B and A are friend. This B and D is a friend. This B is also friend with E, and D actually, well, this is a situation. So basically, so I just given this thing. So basically A is friend with B90, because the thing is that this person is from this is a B, but this B has got a 90 marks, so therefore this is a B 90, so this is basically the friend, and so on and so forth. So if I now try to plot the same thing, I have plotted name over here, I have plotted friends over here, and I have plotted marks over here. Now look that I do not have that problem, you know, because the B, the same name, I can see that the B has the same name, but the friend B, that person has got 90, who has a friend with A, correct? So therefore this B who has 90 has a friend with A. That means B who is a friend with A is 90. So therefore this is the 90 long P. Another B who is a friend with D and E, this B who is a friend with the D and E, they have got these particular marks, which is how much it is, 77. So this is 77. So these are 77 marks. So now earlier we had these lines all on top of each other because it was only one dimension. Now I have two different dimensions. One dimension is name dimension, another name dimension is friend dimension, and now we have a situation that I have separated them because they had the same they have different friends. Now imagine if they have exactly the same name and same friends. Well, then we have to go to a third one, or maybe we should not take the friends as the correlation. Some other correlation we can take, height maybe, or I don't know, something else, right? In fact, we do this kind of things in our real life as well. Suppose both of them have the same name, both has Amit, and we send that Amit has come. Then I say, which Amit? Are the tall one? This tall one, this tall is basically another correlation. I'm actually giving another feature that is connecting it so that this degeneracy is broken. So this is the same thing that we'll be doing in this particular thing. But the question is that these spins, they do not tell me now who is your friend. I can ask them this BC that who is tell me your friend, so that I have this correlation. But the spins, if they have basically a situation like this, that I have A, B, C, D, and E, all these different chemical shifts like this friends A, B, C, D, E, and their names now is a frequency, and they have coupling. The coupling will give exactly the same. The coupling will give splitting, which I have not told separately. I have a situation like this, that I can see that the omega is split into two, so that means it has a coupling with someone. B is also split, C is also split, E also split, and their splitting is nearly the same, exactly the same amount of splitting. So we do not understand that how this particular thing is happening. Instead, if you have a situation like this, that okay, A is splitting like this, B is splitting like this, then C is splitting like this, and D is a single line, and E is again splitting like this, then I can, okay, I understand this. Very simple, because A splitting and E splitting are same, so A and E are splitted, and the B splitting and the C splitted, so basically B and C are splitting. But here, if the splitting is the same, correct, then we have an ambiguity, correct? The similar situation, we have an ambiguity. So how to know this particular thing, that how this who is whose partner, what are the possibilities? Maybe A with coupling with B, C coupling with E, D is fine, D is single, or all these different possibilities are there. So let's see, suppose this student, they cannot tell you the first, like the spins cannot tell you who is coupling with what. Suppose these friends cannot tell you, they cannot speak, or they don't know English, and you know only English, correct? They know only Chinese, maybe, for example. So then I said, fine, you don't have to tell me, but at least you can write your name, correct? They said, yes, I can write my name. So what I'll do is that I'll give them this particular sticky notes, correct? I just give them notes, and I'll simply say that, well, you write your name, you just write your name, and then you do not have to tell me who's friend. You just give your sticky note after writing your name to your friend. And that they did. So basically what they did is that, let me see. So this A has written A, B has written B, C has written C, D, and E. Then they will be changing. So this A and B will be sweeping. So this particular thing will be done. So this A will come here, B will be coming here, C and E will change, correct? I have just taken this particular situation. So I have just made the situation simple. B and A are friend, C and E are friend, and D doesn't have any friend. This boy doesn't have any friend. So therefore, the D has kept its own stick. It cannot just give it. E has given to C, C has given to C, like this. Now we have got this particular thing. And now I'm asking, after you exchange it, you basically write your name again. I said, okay, it's fine, I can write my name again. So A writes her name, B writes her name again, C writes her name again, D writes her name again, and E writes her name again. Okay. Now I collect these sticks. They have not told me, correct? They have just written their name twice. So they have just written their name twice, and they have just exchanged their slip among their friends, like kids do, correct? But now I have collected these chits from there, and I said, okay, so now I can understand that B and A are friend, and that is obviously A and B. B are A, B that friend. E and C are friend, so C are E. And D, oh, he has written his name twice. That means D doesn't have a friend, correct? So similarly, if I now do the same thing over here, so what I do is that I'll tell you this particular one step is called the distribution of sticky node. That means I just created one 90-degree pulse, and I have just created a magnetization. So each of this spin has got their own magnetization created ready by this pulse, which is applying to all. And that is kind of, I have just distributed the sticky nodes to them. Then during this time, this is called the evolution time. During this time, each one of those magnetization is evolving with its own magnetic this Larmor frequency. So A is evolving with omega A, B is evolving with omega B, like that, like this. And then during this time, this is called the magnetization transfer. So this particular is called a mixing pulse. This mixing pulse is basically creating if you have a particular spin like A, and then you have another spin like this, suppose B, and if they have J coupling, then through this particular J coupling, magnetization can be transformed from one to spin to another spin. That is similar to as if one kid is giving his or her chit to the friend, and if someone doesn't have a friend, then he or she retains her cheat with his cheat with him. So similarly, if I have a particular spin like omega, like D here, omega D, and this, it cannot transfer its magnetization to anyone because it is not J coupled to anything. So what will happen is that it will create the magnetization here. It will create the magnetization. It will go through the thing like omega D will go through but as it cannot transfer to anyone, during this next time it will basically go through the same magnetization again, like omega D twice. But what this one, the omega A, this particular first time it is evolving with omega A, but then it is transferred to A is transferred to B, correct? So therefore A has been transferred to B, and the next time the cos omega B has been thing. So therefore we have now the frequency omega S first, it came from here, and then it is the B. So therefore I can clearly see that and then what happens is that if we simply so this is basically the process how to do it. I skip this particular thing, it's not necessary. So therefore I do not have, I can see that. So now if we just plot this particular thing, what will happen is that if you just plot this, then it will have, basically if you just Fourier transform it, then if you have omega A here or here, and if you have omega B over here, these two frequencies, you'll find because of this particular signal that is coming, cos omega AT1, cos VT, you'll be getting a peak like this, which is exactly at omega A and omega V frequency. And that is how this any kind of 2D works. So basically for any 2D, the main thing is this particular mixing time. So this mixing will take the coherence or magnetization from one particular spin, and it will put it to another spin. Now this particular transfer can be done with different things. If it is done with J coupling, then this question, this particular 2D will be called COSY, correlation spectroscopy. If this is done using dipolar interaction, there is another type of interaction, that means two dipoles interact in space. So if it is done with the dipole interaction, then the same 2D is going to be called a NOSY. So therefore, what type of interaction or what type of coupling you are exploiting to transfer the magnetization from one spin to another spin, which are called coupled, either J coupled or dipolar coupled or quadrupolar coupled. Some amount of coupling you need to have, otherwise multidimensional thing will not work. So this particular thing is done in 2D, and this is how this correlation being done. That means A and B are correlated, J coupled or correlated. This is the thing. So therefore we can clearly see that although we have now this splitting and this splitting, A and B are exactly same, but as we have a peak over A and B here, and then if you have another peak, which is basically, suppose say you have a omega C here and omega C and E, omega E here, so you'll get a peak, another peak here, and then suppose an unfortunate omega D here and omega D here, and that omega D will be having a peak with itself. It will not have any cross. So therefore, now we have a situation that we can clearly see that omega D is with L alone, so it is not coupled. A is coupled with B, C is coupled with E. This is E, this doesn't look like E, and so on and so forth. So this is coming to the cozy. So this is how the 2D is done. Well, this is how the 2D signal is generated. This is not necessary. I was talking in that particular, that was a 5-day long teaching on 2D itself, so I had time to do this. So anyway, so this is how this particular 2D is done. Now the question is that this is basic idea. If anyone is having any doubt or any question, because 2D generally, whenever I teach 2D, there are a lot of question comes, because this concept of 2D is not that easy to grip, to have a grip. And one more thing I should tell you that okay, this omega 1 omega t is there, but let me so this is basically a kind of a plot which is having a 2D. So the thing is that you can see this plot. I have this peaks which are kind of on a diagonal. Okay, so that means I have, suppose this one is some spin 1, this one is some spin 2, this one is some spin 3, and this one is some spin 4. So then I can clearly see that I have a cross peak. So this is basically 1 2 cross peak. It's become basically, I can see that this is the frequency between 1 and 2, and this is a 2 1. So if 1 is friend with 2, then 2 is friend with 1. So it's always like this. And I can see that now 3 and 4 are also coupled, because 3 and 4, so this peak is called a 3 4 peak. So this is a 3 4 peak, and this is a 4 3 peak. So basically, again, if 3 is friend with 4, 4 is friend with 3. So this is the peak. Now the question is that if they really have friends, right, then how come they also have peaks like this? This is called as if this particular one is as if 1 with 1. So this is basically again 1. This is 1, correct? So this 1 with 1. Why this particular thing is happening? This is happening because this particular discussion that I was talking about here, what happens that you write your name on a sticky note, and then you give this entire sticky note to your friend. That's because it's a sticky note, you can give it to your friend. But when magnetization transfer is happening through J coupling, I have created a magnetization on A, but that is not entirely going to be, only part going to. If you have to make this entirely going to be, this time has to be very long, and then relaxation will be talking about next class. The relaxation will kick in and we'll have problem. So this T1 is not very big, is not very long. So therefore, the entire transfer of magnetization from A to B does not happen in this particular situation. So a part goes there, but a part is written there. So that means some amount has come here, which has A, B thing, but a little bit of remaining with it itself as well, and that will be again having A type. So therefore, A type and B type, this thing will also be there on top of the transfer. So the transferred one has got this peak, but the non-transferred one is this peak. So the T1 evolution is small and it's not very long. So therefore, a little bit of remaining with them. And this is basically contribute, but in general, these are the same thing. So this is basically, I have the diagonal over here. So basically, this is the diagonal like this. So this is one diagonal peak. This is one diagonal peak. This one is a diagonal peak, and this is a diagonal peak. And the rest, this one, this particular thing, this one is a cross peak. This is a cross peak, and so on and so forth. So this is basically cozy core. You'll be learning about cozy. I have seen this. Your syllabus has cozy, but that time probably will not be going too detailed onto how this particular thing happens, and that is how this. But you'll be applying them. So anyway, so if you have any doubt, the students, you have any doubt on how 2D works, or any idea, any sort of doubts on 2D, you can ask me, or anything. I'll be happy to tell you.
Yes, yes. Exactly.
Hello, sir.
Yes.
Professor, yes.
So I have just a doubt.
Yeah.
So you have cos omega A T1 and cos omega B T1 multiplied. Is there any chance there will be a phase difference so that the whole thing will be zero?
What do you mean a phase difference?
That means suppose in one case cos is 90 degree, in other case cos is 0
Oh
degree.
no, okay. So if you are really asking me up to that, then I have to really go through this process. So then only I can tell you. So that this particular thing is there. So basically, what I'm doing is that generally this is basically so it will not happen. It will not happen in this particular way. So I have a signal. It's called an FID, a free induction decay, is an MR signal. An MR signal basically looks like this. So it has a particular A as the amplitude, correct? So they start from this A and then slowly it decays because of relaxation. Relaxation we'll learn tomorrow. So this A. Now what happens is that this particular T1, how it is done is that this T1 is to a fixed number I have given. So basically it starts from 0, then it gives a certain values, and then it is increased to a slightly larger value, and then particular thing, and then this whole thing is getting repeated. So if I just fix this value to a some value like T0, then the whole thing, the cosine omega 0 A T1 0, this becomes a some value, some value between 1 and -1, because cosine is always between 1 and -1, and that is becoming, then it is transferring here. So therefore, instead of having this signal intensity which is starting with A, it will each time it will start with A times some cos. So it will be A times cos some omega 0 A and T1, and T1 varies. So as I'm varying this intensity, this particular, the amplitude is varying. That is how a 2D actually is recorded. So this amplitude is basically, it is almost like a signal which is amplitude modulated, and then amplitude modulation is done by taking a different values of T1 and this frequency is given, and then this whole data is a 2D data, and then you have to do a two-dimensional Fourier transformation, and it's fine. There phase is there, but not in the context that you are talking about. They will cancel each other. Not like that, because these two are T1 and T2. If you remember, this is a T1 and this is 2. So these two are two independent time variable. I didn't want to go into that complexity, but yeah, as you have asked, so I told you a little more.
Okay, thank you, sir.
Yeah.
And participants, any question? You can directly ask. Chat box, nothing is there. Is there any? It's unmute, no? Hello, participants. Or you can put your question in the chat box. Anyone? Okay. Jyotish, I have no questions. Anyone having any question?
Okay, if there is no question, I'll just tell you one particular thing is that what's the difference between the cozy and nosy that I was talking about, right? Because I have about 5 minutes more. So
Okay.
yeah, so this cozy and nosy, this one is called this J correlated spectrum, another is 2D, another is called the dipolar correlated one. The dipolar one is very important for structure determination, because as a chemist or a biologist, you must be doing some kind of structure determination, whether it's a structure of a small molecule or structure of big molecule, you will be doing. How structure is done. So basically the idea is that if you have a molecule, if you have a molecule which has a shape, correct? Suppose you have a protein, correct? This particular thing, it has a three-dimensional shape. How generally it is being done, that how this three-dimensional shape can be done. So what happens is that if you just now can break this particular molecule in units like this, which is basically the amino acids for a protein, and then if you can find out that the distance between any two amino acids, or maybe distance from ith one to the jth one. So the distance I to the j, where I is one particular amino acid. Suppose this is the amino acid 1, and then amino acid maybe 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10. Right. So if I now know the difference between, this might be 200, it's a very long one. So if I now know the distance of each one, 1 to 6, 1 to this, 1 to that, so that means I have the distance information of each I and j, then I can actually create this model, correct? So this particular thing means that I need to know the distance between each amino acid with another amino acid in the same molecule. And then if I have all this distance information, then I can put this distance information into a software. We cannot do it ourselves because it's a very complicated one. So many constraints are there. But somehow computer can do it for us. And this is how a protein structure is actually done. But now the question is that how will you get this distance information? This distance information is done from NOESY, N-O-E-S-Y. So it is, what it is done is that you basically create one omega A. Always you start from the frequency of one particular one, and then you will be taking this to the T1 one. So basically it is going to be giving, it will write its own name. That means it will evolve with its own frequency, omega cos omega A, and then it will be getting transferred, correct? Now this transfer is going to be a dipolar transfer. That means how this dipole, that means two dipoles are interacting only when they are close in space. If they are far apart, basically if it is more than 5 angstrom, they do not interact. So only those spins which are spatially in space within 5 angstrom, this transfer will happen. That means what I can see is that, suppose this one, this particular one, let me give a slightly different color. This particular blue one and green one and this one, they are close in space. Although line wise, look, this is basically this is going to all the way like this, and then it is coming. But somehow because of this fold, they came close. So therefore, if I do a transfer here, that if omega, this is your omega A, suppose this is your omega A, and suppose this is my omega B, correct? Then because of they are close in space, a transfer between omega A and omega B will happen. Dipolar transfer. So this is called a dipolar thing that is being exploited in NOESY. So therefore you'll get B, and therefore when you be plotting this thing, so you'll get a omega A frequency over here, maybe a omega B frequency over here, and you'll get a peak here in between omega and B. But then there, the peak between omega A and omega B is not going to be interpreted as if they are J-coupled, because you are doing NOESY, not COSY. But they'll be interpreted that they are close in space. So therefore, if you just take this thing, this is basically a peak like this. So you have peak. And if you just take the area under curve, that means the stronger the peak is, the closer they are, because that the dipole interaction is much stronger. So just by looking at the position which is connected to which, that means they are close, and then taking area under curve of the peak, that means how big the peak is. If the peak is very small, then maybe the very feeble thing, they are not fine. So therefore, by just looking at these things, if you just put into the software, they will actually create a model like this. So if they are very strong peak is there, like for example, if you have another one over here, and that will give a very strong peak. So this is going to give a strong peak, for example, but this will not give a strong peak with this one because this is far apart. So therefore, those which are giving a strong peak, the computer will bring those few amino acids trying to closer, and then they will try to find an optimum solution which is consistent with all the distance constraints. It's not violating anyone. Then that is basically the structure. So this is how protein structure determination is done. Well, I have oversimplified it, but this is basically how distance structure determination of biomolecules are done using this particular 2D. It's not done as 2D, it's done as 3D because too many signals. But nonetheless, 2D, 3D, the concept, the basic concept of first create magnetization, then have it some T1, then transfer it, either dipolar coupling or J coupling, then evolve again. Therefore, you get a peak between omega A and omega B. or omega C and omega D, something like this. This basic concept is everywhere in all multidimensional experiments. And that is what I hope you understood today. Okay, so it's nearly time. So if is there any more question? If not, then we'll stop it.
I think yeah, the participants are not asking anything, so that means they understood whatever.
Well, I tell my students that in two different situations, students do not ask any question. First, they have not understood anything, and they have understood everything.
we take it for. So we take it positively. They understood.
Okay, they have understood everything. Okay. Fine.
Okay. Still, participants, if you have any questions, you can directly send email to Professor Ghosh. He will be happy to respond to you.
Yeah, sure.
Okay. Okay, take that up this privilege, write to him directly, and get your doubts cleared. Okay. Okay. With this, let us thank Professor Ghosh for the nice talk, nice presentation.
Somebody asked just something.
Which one?
I just saw somebody gave a.
Will this multi-dimensional experiment work in the case of protein structure determination?
Yeah, of course. Protein structure determination cannot be done unless you have multidimensional NMR. Much more complicated one. For protein structure determination, you need not 2D, but you need 3D, 4D, 5D. Actually, much more complicated one because there are too many residues are there. So definitely you need multidimensional. Without multidimensional, it's just not possible.
Okay. Rutisha, I think you got your answer. I think she's happy with the answer. Okay, good. Anyone else? In YouTube? Anyone? No. Okay, Professor Ghosh, I think it's okay. Thank you very much then.
Okay.
So our next lecture will be on Tuesday, right?
Yeah.
Tuesday at 4 o'clock.
Yeah.
Not yet.
Sure.
Okay, sir. Okay. Thank you. Thank you.
Thank you.